Hey guys, welcome back to another Math HL video. And now we'll be discussing trigonometry, and I know all these formulas look kind of daunting and terrifying, but let's go through them together and we can actually understand each one of them. So let's start with a regular triangle, any triangle with angles small a, small b and small c, and sides, big A, big B and big C. So from this triangle we can work out many things, and we'll just have to go through all the formulas we know. So this is the first one, which is known as the sine formula. And that says that sine of small a, this angle here, over the side big A, is equal to sine of small b, this angle here, over big B. And that's the first one, and that's also likewise appropriate for sine of small c over c. And this can be then arranged to give you whatever you need. For example, if you needed the angle A, the angle of A, you'll multiply this side all by the capital A side, and then do the inverse sine of that. And likewise, if you needed one of the sides, you could just rearrange and find what you need. And this brings us, then we can look at the next formula. So let's say you only knew two sides, two adjacent sides, and the angle between them. For example, B, C, and small a. Now we can use another formula known as the cosine formula, since this formula cannot be applied using the knowledge we have. So using this formula, we also get another formula. And this is the a squared, this side here, is equal to b squared plus c squared minus the product of 2 times b times c cosine of a. And the derivation of this formula is a lot more complex and beyond the depth of this video. And as you might have realized, this formula is kind of similar to the Pythagorean formula, using a squared equals b squared plus c squared. And you might have realized that if a is equal to 90, and we did have a right angle triangle, this would all equate to 0, giving us just a squared equals b squared plus c squared, which is Pythagoras' theorem. And then the last thing we can infer from a triangle, so like this, also considering you have two adjacent sides b and c, and a, is that the area is half of b times c sine of a, this angle here. And likewise, if this was a 90-degree triangle, then you can just work out area to be, since sine of 90 is 1, just half b c, or half base times height. So these are the three formulas you're going to use when determining sides and angles about triangles, and they don't need to be right angle triangles. This can be applied to equilateral or isosceles, or just scalene in general. And now, this brings us up to some trigonometry identities. These are the basic format, and let's go through them. So the first trigonometric identity is sine squared of theta plus cos squared of theta is 1. And again, I can't really prove this to you, but this is a formula you must know, and you must memorize, and you must know how to rearrange. For example, you must know what sine squared of theta is equal to 1 minus cos squared, and likewise, cos squared of theta is equal to 1 minus sine squared of theta. And that is the basic formula. And then another important trigonometric identity is tan of theta is sine of theta over cosine of theta. And again, you must once again know this, and this is due to the way it was one of the relationships. And then if tan of theta is equal to that, then cotan of theta is equal to cosine of theta over sine theta, which is basically just the inverse of this. So you might have realized this is also equal to 1 over tan of theta. And then the last two formulas, identities we need to know to really expand our knowledge, is secant of theta, which is equivalent to just 1 over cosine of theta, and cosecant of theta, which is equal to 1 over sine of theta. And if you've been following along, you can realize we can derive some more formulas from these identities we have here. So let's start with the Pythagorean identity known as sine squared of theta plus cos squared of theta equals 1. If we were to divide all of this formula by cos squared of theta, you'd get sine squared of theta over cos squared of theta plus 1 over 1 over cos squared of theta. And this again can further simplify to give us another formula. So this is equal to sine of theta cos theta, all of it squared. This is equal to 1. And this is also again equal to 1 over cos theta all squared. And looking back at the identities we already derived, sine theta over cosine of theta is known as tan of theta. So let's just go over that. So it's tan theta squared plus 1. And this 1 over cosine of theta is known as secant of theta, which is secant of theta squared. And this again can just be written as. And this is another Pythagorean identity that you only need to use when you only know, for example, secant squared or tan squared. And likewise, again, if we go back to the original formula, let me just erase this for you and we can go back to another proof. Is if we divided this formula all by sine squared. So once again, let's go through it. Sine squared theta over sine squared theta will give you 1. Plus cos theta plus sine theta all squared. And is equal to 1 over sine of theta all squared. This is just dividing the first step, everything divided by sine squared of theta. And now, once again, by looking at the identities we have already came up with and the ones we know, we can write this as cotangent of theta. And we can write this as cosecant of theta. And these two trigonometric identities are also ones you're going to need to know, and you're also going to need to be able to work with them.